Dear students, let's continue our practice on mathematics. Today's topic is natural numbers, prime and composite numbers, some notations from mathematical logic. So, let's begin with the definition of natural numbers. What is natural number? Natural number, which numbers we can use to count. For example, we can say one apple, an apple, or 2 apples, or 3 apples, yeah? We cannot say -1 apple or 0 apple. Which we use to count, we'll say natural numbers. These numbers we say natural numbers. So the natural numbers is denoted by the set of natural numbers denoted by n, capital N, and it is 1, 2, beginning from 1, 1, 2, 3, 4, etc. Yeah, they are they continue, so it is infinity. So and now this is natural numbers. Here I think all of you know how to do operations on natural numbers and etc. There are operations adding, subtracting, multiplication, division, and etc. Powers. So now, prime. I want to talk about the prime numbers. So the prime numbers. Prime numbers. It is which numbers. They have only they divisible by itself and by So, and now I want to talk about prime numbers. So, prime numbers, the definition of prime number. Prime number, it is which number divisible only by itself and 1. For example, the least prime number, it is 2. Because 2 is divisible by 2 and 1 only. So, by itself and 1. The next one, it is 3. So, 3 also divisible by 1 and by 3. They have only 2 divisors. Such kind of numbers we call prime numbers. The next one is, which one? Correct, it is 5. Then, 7. Look here, pay attention. Only 2 from even numbers is prime number. Other even numbers cannot be prime because they have another divisors also. So minimum they divide by 2 because they are even numbers. And look here, not only all odd numbers are prime. I mean, all odd numbers are not prime numbers because here we have 3, 5, 7, and the next one. We cannot take 9 because 9 is divisible by 1, by 3, and by 9. So has 3 divisors. That's why we cannot take as prime number 9. So the next one is number 11. The next one is number 13, and etc. You can continue this this sequence of number. They are prime numbers. And now, why we need the prime numbers? To write prime factorization of number. So, to find prime factorization, we need to recall here rules of division of number. So, for example, which numbers are divisible by 2. We said about it, this is even numbers. So, even numbers divisible by 2. And the next one, all even numbers. And next, two numbers through which numbers are divisible by 3. We cannot say all odd numbers. Here, what numbers is divisible by 3? So, it is, for example, 9, it is, for example, 12, it's, for example, 15, yeah, etc. So, here, look here, we have law in this case. So, if the sum of digits divisible by 3, such kind of numbers divisible by 3. What means sum of digits? What is digit? Digit, it is from 0 till 9. They are digits. In this case, what kind of digit we have? 1 and 2. If you add them, it is 3. And 3 is divisible by 3. That's why it's divisible by 3. For example, any other example, 216. Let's find the sum of digits. 2 plus 1, it is 3. 3 plus 6, it is 9. And of course, 9 is divisible by 3. So this number is divisible by 3. Because of 2 plus 1 plus 6, it is 9. I think it's clear. So now, number 4, to number 4, what kind of numbers is divisible by 4? Here also we have the law of division by 4. It is when the last two digits together give to us the number which is divisible by 4, such kind of numbers is divisible by 4. For example, 2332, for example. I said the last two digits together. So this one, yeah, it is 32. And you can see 32 is divisible by 4. So it means this number is divisible by 4. So it is law for number 4. And now, next one. Number 5. To number 5. What kind of numbers are divisible by 5? So here, it's very easy. If the number ends with 5 or 0, it's divisible by 5. So, for example, 20, 0 here, or 175, for example, 5, yes? So, they end with 5, 5 and 0. Okay, number 6 now. To number 6, which number divisible by 2 and 3 at the same time, they are divisible by 6 also. For example, here, the previous one, example, 216. It is divisible by 3, we showed, yeah? And now, it's divisible by 2 also. Because it's even number. So, it means this number is divisible by 6. And we have the next one, it's 9. 9, it's close to 3. Here, we need to find again sum of all digits, and it should divisible by 9. For example, 378, for example. The sum of digits, it is 3 plus 7, it is 10, and 10 plus 8, it is 18. So it's divisible by 9. Because sum of digits is divisible by 9. And we have 25, for example, also. So if number ends with 10, it's very easy. 10, when it ends with 0, for example, yeah, this is divisible by 10. And 25, when the number ends with 0, 0, at the end, and 25, 50, and 75, they are divisible by 25. Okay, now, we need to open a new. And now, return to prime numbers and prime factorization of numbers. For example, if we consider any number, 72 for example, yeah, and do prime factorization this number. And how can we do the prime factorization? This is very easy. So 72, we begin from 2, if it is divisible by 2. We need to move by this sequence. What was our sequence prime numbers? 2, 3, 5, 7, 11, 30, etc. Yeah? So we need to move by this sequence, by order. So here, beginning from 2, yeah? Is it divisible by 2? Yes, because we know this is even number. So, divide by 2. It is 36. And now, 36, is it divisible by 2? Yes, it's divisible by 2. So, it is 18. The next one, 18 also divided by 2 can. So, 9. And now, 9 is not divisible by 2. So, we need to move to the next one. The next one is 3. 3, 9 is divisible by 3. So, this one. Now, the next one it is 3. And 3 is divided by 3 only, because it's prime number. And 1. We'll continue. Let's clear this one. So we will continue till 1 here. Till 1. Now, we can write 72 as product of these numbers, because we divided by these numbers, and we'll write 2. We can write 2 the third power, because here we have 1, 2, 3 third power, and times 3 squared. 2 times 3 we have. So answer 72. The prime factorization of 72 is 2 cubed times 3 squared. This is we call prime factorization of numbers. And for example, next example, any example here, 100, for example, 80. This is divisible by 2. Let's write to this part of whiteboard. So 180. Again, beginning with 2, it is 90. Again, 2, 45. Yes? So now look here. What we need to divide? Not 5. Because 45 is divisible by 3. Because 3 plus 5, the sum of digits. Why we need the laws of division? So here we will use it. So 4 plus 5 is 9. And 9 is divisible by 3. So here we need to write 3. We need to keep our order. 2, 3, 5, 7, etc. Not write first 5, then 3. Okay, here we have 15, and one more time 3 we get 5, and now 5 is only, this is prime number, it's only divisible by 5 and 1. So we can write here 180, it is 2 times 2 squared, 2 times 3 and 5. This is prime factorization of this number. Okay, now we have the definition of number of divisors. Number of divisors. For example, if you take any number, for example 12, yes? How much divisors it has? 1, 2, 3, yes? Then 5, not 4, 6, and 12. How many? 1, 2, 3, 4, 5, 6. 6 divisors it has. Number 12. But we will not do this work for example, we have 2136, yeah? How many divisors it has if we have a question? We will not do the same work for this number also. Count all divisors. So we have method to finding number of divisors. For this one, we need to do prime factorization of this number. For example, let's show by 12. Firstly, 12, it's divisible by 2. Firstly, 2, but then 6, again 2, 3, 3, and 1. So, 12, if you write here, it is 2 times 2, and product, and multiplied by 3. Okay, now, how can we find the number of divisors? We need to prove it is 6. Because we have 6 divisors here. We don't have any other divisors. Okay, for this, we use this symbol to denote the number of divisors. Tau. This is from Greek alphabet. This is tau. And tau 12. It means number of divisors of 12. So, here, look here. This is prime factorization of 12. And here we have what? Degrees of numbers, yeah? The prime numbers. So here we have 2 degrees. And here we have just 1. So, to find tau, we need to add 2 powers 1 and multiply to next power adding 1. Like this. So it is, here we have 2. So it is 2 plus 1 times, the next one is 1. 1 plus 1. So 3 times 2, it is 6. We got our 6. Is it clear? So, power plus 1, the next power, times the next power plus 1, etc. And now, let's consider the next one. For example, any other number. Let's do for this example. 180. Because we have already prime factorization. Okay, 180. It is, what was our prime factorization? 2 squared, 3 squared times 5. 2 squared, 3 squared times 5. So here, now, how to find tau? Tau for 180, it is, look here now, 2 powers, pay attention to powers, 2, 2, and here we have just 1. So, 2 plus 1, 2 plus 1, and 1 plus 1. So it is 3 times 3 times 2. We get the answer 9 times 2, 18. So 180 has how much? 18 divisors. Okay. So this is the number of divisors. Okay, and now let's continue. So the next topic is sum of divisors. Sum of divisors. So we consider the number of divisors and now sum of divisors. For example, again, an example number 12. The sum of divisors of 12, it is, we can see here, the divisors of 12. It is 1 plus 2 plus 3 plus 4 plus 6 and plus 12. Yeah, this is sum of divisors. So here we have 5, 5, 10, 20. So it is 18, 28. So sum of divisors of 12, it is 28. And now, how get, for example, 180? We will not find all 18 divisors and find the sum of these divisors. To find the sum, we have also formula. So, again, let's write the divisors of 180. It is 2 squared, 3 squared times 5. Okay, and now to find the sum, let's denote by S, the sum of divisors. And here, again, we need to consider powers. 2, 2, and 1. Yeah, here 1 we have. So now, look here. Now we have the powers and we have the bases of powers. So the first one is 2. We will do by so for all of them separately. So 2, write 2, this base, and power of this 2, 2, add 1 to the power and subtract here minus 1. So one more time. And here base, first base 2, first prime number, then the power of this prime number plus 1 and subtract 1 over all of them. Then divide by this first prime number again 2 and subtract 1. 2 minus 1. Clear? So, and the next one, similarly, here we have 3. 3, the power is 2 plus 1 minus 1. Here also 3 minus 1 now. By the same way, for number 5, it is 5, the power of 1 plus 1 minus 1 here, and 5 minus 1 here. So, it's equals to, here we have 2 minus 1, it is 1. Here, 2 the power of 3 minus 1 times 3 the power of 3 minus 1 over 2 times 5 the power of 2 minus 1 over 5 minus 1, it is 4. If we continue, so we have here 8 minus 1, it is 7, times 3 cubed, it is 27. 27 minus 1, it is 26. 26 over 2, it is 30. Times 5 times 2, it is 20. 5 times 5, it is 25. 25 minus 1, it is 24. 24 over 4, it is 6. If you multiply all of them, we get the answer. So this is the sum of our divisors of 180. If you want to check for 12, here, for 12, let's consider 12, and here we have 12 had divisors 2 squared times 3. So for them as it is now 2, first one is 2, the power is 2 plus 1 minus 1 over 2 minus 1 times for 3 now 3 times 1 plus 1 minus 1 over 3 minus 1, and we get here 1, 2 cubed, it is 8 minus 1, it is 7. The first one is 7. The next one is, here we have 3 squared, it is 9. 9 minus 1, it is 9 minus 1 is 8. 8 over 2, it is 4. So 7 times 4, it is 28. So we get our 28. The sum is 28. By the formula also we get 28. So this is formula for the sum of divisors of number. By this way we can find for other ones also. So I mean for big numbers also. Let's write here one more example. For example, number A, any number which has divisors, for example, 2 cubed, 3 fifth degree, for example, yeah, 7 and 11 squared, for example. And here we need to find tau. So the number of divisors of A. Here, what should we use? Again, this recall this definition of tau. 3 plus 1, the power plus 1, times 5 plus 1, times 1 plus 1, times 2 plus 1. Yes? Adding by 1 for each power. So, it is 4 times 6 times 2 times 3. So this is answer of our tau. Here we have 4 times 36 or 144. Okay, now find for A the sum of divisors. So A has 144 divisors, and we need to find the sum of these 144 divisors. We have formula, so it's very easy by the formula. Let's find SA. It is 2, 3 plus 1 minus 1 over 2 minus 1 times, next one, 3 the power 5 plus 1 minus 1 over 3 minus 1, then 7 the first 1 plus 1, because it's first power here we have, minus 1 over 7 minus 1, And the last one is 11. 11. 2 plus 1 minus 1 over 11 minus 1. If you simplify our expression, we get here. So this is 2 fourth degree minus 1. Let's write just these powers. 2 fourth minus 1 over 1. Then 3 6 minus 1 over 2. I think it's clear. And 7 2 minus 1 over 6 times 11 third degree minus 1 over 10. So this is, if we calculate all of them and find the multiplication of these numbers, we get our answer, we get our S. The next time we'll continue our practice. It was the last example. Thank you for your attention. In addition, I want to give some notations from mathematical logic. Here, main logic symbols. The first one, for example, this is implication. Here you can see we denote by this symbol or these two ones. Usually we use the first one. This is implication. Reads as implies, or if the situation that. Explanation here. A implies B is false when A is true and B is false, but true otherwise. So, for example, x is 2 implies x squared is 4 is true, because if x 2 we can get x squared is 4, it is true, yes, but x squared is 4 implies x is 2. This is not true, it's false in generally, because here we have squared, and since x could be minus 2 also. Now, the next one. Equivalence. This one, the first one, we usually use the first one, equivalence, or the second one also. Reads as if and only if, or like this, if, means the same as. So this is from the group propositional logic symbols. A equivalence B, or A if and only if B is true, only if both A and B are false, or both A and B are true. So, it is true only if both A and B are false, or both A and B are true. For example, x plus 5 is y plus 2. This is equivalent with x plus 3 is y. Here, it's true. If it is true, this is also true. Because you can see here x plus 5, and we can write, instead of this one, x plus 3 is y. If move 2 to the left side. Okay, now, next one. The next one is negation. And we denote the negation usually by this symbol, the first one, negation it means. It reads not. This statement, negation A, is true if and only if A is false. So, for example, we have double negation, not A, it is A, or X is not equal to Y, it is not X equal to Y. This is not a negation, not, symbol not. I think it's clear. Okay, now let's move to the next one. Domain of discourse. We denote by D. Domain of predicate, we call it. D, for example, D is R. R, it is the set of all real numbers. And now, the next one. Logic conjunction, it's called. So, it is and. Read and. Usually we use this one, first one, and. The statement A and B is true if A and B are both true. Otherwise, it is false. For example, n is less than 4 and n is greater than 2. It's equal with n is 3 when n is a natural number. Obviously, here n is less than 4 and n is greater than 2. It means n is 3 if n is natural number. We don't have any number between 2 and 4, any natural number, I mean. Okay, the next one is logical disjunction. And often we use this one, disjunction, for disjunction. It is or. Disjunction, it means or here. We read or. The statement A or B is true. Definition. If A or B, or both of them, are true. If both are false, the statement is true. For example, n is greater than 4 or n is less than 2. It's equal with n is not 3. It's not equal to 3 when n is a natural number, because usually we have we only get 3 here because n is greater than 4 or equal and n is less than 2 or equal. Between them we have or, the symbol or. It means n is not equal to 3. And now the next main one, it is the symbol of for all. The first one we usually use. Universal quantification we call. We read for all, or for any, or for each. For example, for all x, px. So px means, px is true for all x. One more time. For all x, px. It means px is true for all x. For example, for all n belongs to natural numbers, n squared is greater than or equal n. It is true for all natural number. Next one, existential quantification. This symbol, there exists. We read, there exists. So, there exists x such that px. It means there is at least one x such that px is true. For example, there exists n belongs to natural numbers, the set of natural numbers, n is even. Of course, we have at least one even natural number. It is true. The next symbol, it is uniqueness quantification, or there exists exactly one. This symbol, there exists exactly one. For example, here the explanation, there exists exactly one x such that px. It means there is exactly one x such that px is true. For example, there exists exactly one n belongs to natural numbers. N plus 5, it is 2n. Here we have exactly one solution of this equation. It is, for example, n is 5 here. If you solve by 5. And the next one, definition. Usually we denote by this first symbol, definition. Symbol of equation and 2 dots. Symbol of equals and 2 dots. Is defined as. We read is defined as. For example, x is defined to be another name for y. Here we call x is defined to be another name for y. For example, here we have the example, cosine, hyperbolic cosine of x. This is function, hyperbolic cosine of x is defined as this function, e to the power of x plus e to the power of minus x over 2. I tried to give you some main logical symbols. Thank you for your attention.